So first of all, thank you very much for the organizers organizing this nice workshop and for the invitation to be here. It's a pleasure to be here in Vienna and it's a nice audience. Yeah, so this is work that I did with my PhD student, Hyunho Kim. I should mention him explicitly. It's on the arXiv. If you should ever see him on a candidates list for postdoc position, hire him. He is really excellent, particularly if you have conceptual work. He's really, really good. And I should say that a lot of the ideas actually, or the big idea that analyzes is probably due to Konrad and Thomas Nikolaus. So there's references to Konrad's talk as well. Okay, so a little bit of expectation management, that's probably a good idea. So I won't give a mathematical talk. There won't be almost no theorems, but what I do is I present a framework for T-duality, so perspective on how you describe, or how you can describe T-duality, in particular the non-geometric cases. And the story has a lot of loose ends simply because the project was initiated as a project for my PhD student. We have a big project on the double copy, and a lot of us needed to catch up on things, and he was, in a sense, unemployed. He didn't have anything to do with at that moment, so we started this. And then the paper grew and grew and grew, and now it has 60 pages, and we said, okay, we leave it at this and just put it out. But there is, while the constructions are fine, there are a lot of open mathematical questions. Not so much mathematical questions, I just would say more questions about the physics, and one should explore to what extent our constructions meet the expectations. So if you have any questions, comments, I'm very happy to receive them. This is very much a work in progress. It's like the first project, the first paper in a longer research program of describing these things, also then extending to U-duality. So if you have any questions or comments, you're very welcome to ask them. Also, I should say I'm not claiming to be an expert on T-duality by any means, so if you have comments of misrepresentations, interpretations on my part, please do so. Something positive, what I very much like about this this paper is we use a lot of higher structures and by categories and then by functors and so on, but everything is very, very explicit, so you can boil down things to very pedestrian level. Everything is very much at the levels you can give explicit co-cycles for all of these bundles that we have. All the formulas are harmless, all the groups that are involved are really, really harmless, right? So you can really make everything explicit to a degree that you usually can't if you involve higher structures, right? Or where it's at least very difficult to do so. No, this direction. Okay, so T-duality, everybody knows. If you have a string theory on a background with your one isometry, then you get a T-dual partner. And in the low energy limit that we'll focus on here, you get corresponding supergravity, and that contains a B field. And as you know, or as people know, since Gawecki is that this B field should be regarded as a connective structure on a gerb. So what I'll be dealing with are what sometimes are called geometric string backgrounds, at least in the first part of the talk. So we have a Riemannian manifold, Lorentzian if you like, I'm not sure if it makes much of a difference. Riemannian manifold, manifold with a metric. You have a principal or an affine torus bundle, so we generalized this a little bit to a affine torus bundle as well in our discussion directly, with connection, and you have an abelian gerb on the total space of that torus bundle, principal or affine, and the abelian gerb has also a connection. Importantly, we ignore all the dynamics, right? There's no equations of motion imposed on this data at all. So it's just literally this geometric data. So it's kind of at the kinematical level, no dynamics at all. Okay, so and then you know the story from topological T-duality. So here we have our string background without the connections in this case. And then as Peter Bauknecht likes to emphasize, that topological T-duality follows from the exactness of a Gaussian sequence. So you have a sequence that looks like this, a long exact sequence. And what you do is you have a gerb over the total space of your principal bundle, right? Characterized by a 3 form in H3PZ. And then you can do a fiber integration down here. You get a 2 form, H2XZ on the base of that principal fiber bundle that we have. And the cup product vanishes, right? But because this formula is symmetric, I can interchange the roles of the Fs. And because I know I map here to the kernel, there must be something that produces this 3 form. So I know that there's actually a 3 form on this dual bundle, which is characterized by this Chern class. And that its fiber integration will produce the original F. And topological T-duality is then simply the exchange of this F and H with this F hat and H hat, right? And of course, in this process, we change the Chern class of the line of the circle bundle, so we can automatically change the topology. Sorry. So we have here a principal bundle, a torus bundle. It's characterized by Chern classes, so we have lots of curvature 2 forms if you want, right? And of course, we have a gerb on that, so curvature 3 form if you want, right? Curvature 2 form of a connection. F hat is the one that you obtain by fiber integrating the curvature 3 form from a gerb along the circle fiber, right? Yeah, sorry. I mean, this story is for principal torus bundles. Yeah, exactly. Okay, and then as yes, exactly. Yeah, that's after T duality. So you fiber integrate the H, you get an F hat, right? It's a cup product, right? Oh, look up in differential geometry textbooks, right? So it's just a cup product. You produce, you have wedge product at the end of the day. Yeah, exactly. Yes. You have this, a theorem tells you that you have this Gisin sequence, right? It's zero in cohomology, yeah. Okay, so. Okay, yeah, sorry, I'm not sure how much of the review I should do because Konrad already did quite a bit. So then there are the T correspondences that Konrad told us about, where you have this full picture. So here we have our original, what I called before P over my manifold, a torus bundle, and in our discussion we then extended also to a affine torus bundle. You have a gerb on the total space, and then you get the dual torus bundle and the dual gerb, and you say that this data is forms a T correspondence. If you form the correspondence space as a fiber product, you pull back the two gerbs, and you see that they are isomorphic and related in a particular way, right? So you, yeah. This is Konrad told us already about this, right? And now the nice idea, and this is the idea that we use and run with, is from this paper by Konrad and Thomas from 2018, that you can define or describe these whole T correspondences in terms of principal 2 bundles. And of course, it's all topological, so you don't have connections, but you just look at principal 2 bundles over the base manifold, and this fully encodes such a T correspondence. Okay, and this is actually very, very nice because, I mean, you package all the geometrical data really up in one object. So that's a very, very nice idea. And it's very nice that this works all together. But there are now 2 open problems in the setup. Namely, T-duality can lead also to non-geometric backgrounds. So you have this classification of backgrounds that you probably know. And it essentially depends how many legs your H to the 3 form has in the T-duality directions, right? You have 3 form, you can count how many legs go in this torus direction along which I want to do T-duality, roughly, okay? And if it has no legs, then the T-duality doesn't do anything, that's fine. If it has 1 leg, then I get geometric string backgrounds. If it has 2 legs, then I can get the Q spaces. Yeah, exactly, yeah. Yeah. No, it's really Tori, right? So then you get the Q spaces, which are locally geometric, and then you get the R spaces, which are not even locally geometric. So these are sometimes described in terms of non-commutative geometry, these in terms of non-associative geometry. And in the paper by Konrad, what's covered is essentially the T-duality for F2 spaces, for F2 backgrounds, between 2 F2 backgrounds, and T-dualities between F2 and F1 backgrounds, right? So these can be described. But now the obvious question is, what about the general case? That's the first question there, right? How to complete this picture. And the other question is, how do I put the differential refinement on these principal 2 bundles so they really talk about explicit metrics and B fields, right? So that's not just a topological T-duality. And then you can ask, why is this interesting or hard? Well, the first thing, in the first problem, the generalization to all of this is that, as it turns out, you need to use groupoids or higher groupoids and augmented higher groupoids. You can't just work with principal 2 bundles, but you need to go beyond that. And it's not too surprising because, I mean, if you have a B field and you do a T-duality along 2 directions, it's roughly Kaluza-Klein reduction along 2 directions, so you get scalars as well, right? So you don't just have 1 forms, which would be in the principal 2 bundle, but scalars, so you get also a groupoid bundle. And then in the R space, interestingly, you need augmented groupoids, which is kind of nice. And the other problem is the differential refinement, and there, what you need to do is you need to modify a little bit the standard connections that you find about principal 2 bundles in the literature. You need to add something that we call an adjustment, which means that you allow for the gauge, for the curvature acquires an extra term, which is actually well known from the physics literature, but it's a little bit, not quite present in a lot of these literature on principal 2 bundles, and that allows you then to put a differential refinement into this picture. Okay, so the outline is, I'll tell you a little bit about principal two bundles and adjusted connections, just to advertise it a little bit more, because at least in the theoretical physics community, there's a little bit of a prejudice against these non-abelian gerbs, and they say non-abelian gerbs, they don't give you anything new anyway, and I explain why this is and what you need to do to get something interesting. Then we first start looking at geometric T-duality with principal two bundles, so differentially refine what Konrad did, and talk a little bit about the T-duality group, how it enters the picture, G, O, N, and Z, and then I explain how you get to groupoids and augmented groupoids. And throughout everything, I can give you explicit examples in terms of this T-duality on Neal manifolds. That's a common popular example when you talk about T-duality. Okay, so principal two bundles, non-abelian gerbs. I don't think I need this slide really in this audience, right? Categorification is clear, right? So you have mathematical objects given by sets, structure, functional structure equations, replace them by category, structure, functor, structure, isomorphisms, and everybody knows how to categorify a group, right? So I can probably skip this and focus on other things. And an example for two group that will be featuring throughout this talk is this two group Tdn that Konrad already mentioned, and it looks like this as a Lie two group. If you prefer two groups in the form of crossed modules, it's down here. But what you see is, this is quite harmless, right? I mean, there's nothing serious going on. There's a U1 factor, which will produce, which is responsible for an abelian gerb part. And then there is an other 2n U1 factors, which are resolved into this Z2n over R2n, which will give you abelian connections along the torus directions of the bundle itself and the dual bundle, roughly speaking, right? So this is the shape that you expect, and this two group is very, very harmless, right? I mean, there's not much going on. This angular bracket is just a bilinear degenerate pairing. It's like one block in the ODD metric that you take, you throw away the other one, create from this a bilinear pairing, and that's it. No, this U1 doesn't talk to it, right? However, what you do have is you have this action of an element here onto an element here, and this will produce additional terms in the U1 factor. This psi m sits in this U1 factor, right? I mean, you have this psi in R2n, which can act on elements here. Elements here are parameterized by m in Z2n, phi in U1, and this action produces this additional term from psi and m in U1. No, it's not an integer, it's U1. It's a phase, right? Right, sorry, this is additive notation, right? So e to the is the U1, right? It doesn't have to be an integer, it's an element in U1. M is an integer, psi is not an integer, right? And right, okay. Yeah, you take exponential 2 pi of this expression, right? Sorry? Yes, that's it. No, but I think the question was whether there's any interaction between the U1 and the other two, right? And you see it in this action. Absolutely, that's what it is, yeah. So topologically, how do you get principal two bundles? I guess a lot of people here know this as well. Essentially, you can categorize any definition of a principal bundle. All of them work, and they lead to more or less equivalent statements. So starting from a surjective submersion, you have a manifold X, and you have some surjective submersion. If you want to think about it as a cover, you construct the check groupoid with its objects, the elements in Y, and morph is just a fiber product, and the evident composition. And then a principal G bundle is just described in this check cocycles as functors from this check groupoid into BG, so the one object category which has G as its morphisms, right? I mean, it's just this picture, and composition here induces the usual cocycle condition on the right-hand side for the group, for the cocycles that describe your bundle. And then equivalences or bundle isomorphisms are given by natural isomorphisms, right? And this picture, of course, has a very, very straightforward higher generalization, right? I mean, the check groupoid is trivially a two groupoid, and now any two group that I have gives rise to one object two groupoid. I just look at two functors. I need to use lax two functors to get something interesting, and then you get principal two bundles, right? And in particular, you also get abelian gerbs, right? The usual abelian gerbs that you know from the literature, right? So this picture is kind of important because this really works for everything. It works for two groups. It works for two groupoids as well. Then I just replace the dot, this star by something more. And it also extends to augmented groupoids, as we'll see later on, right? So the construction there is relatively straightforward, and it's not controversial at all. Then you want to put connections on your principal bundle, and then you work a little bit more. You can do that from various perspectives, and I don't want to go into detail. And there's old papers by Breen Messing and Aschiari Cantini from 2005. From different perspectives, they obtained the same description. And what you get in these papers is the following data. So imagine that your gauge 2 group has this form, right? And you can show that actually every 2 group is equivalent to one of these forms. You get an H on triple intersections with values in H. You get a lambda that glue sets together the 1 form. On double intersection, you get a 2 form on the patches themselves. And you get also corresponding data. And what you notice is that there's something sticking out of this data that they obtained. This is this weird thing, delta here, which is a 2 form on double intersections, right? I mean, here there's a natural hierarchy, right? I mean, when I can trade a degree in my check groupoid for a form degree, right? You see, okay, I go 1 down here in Y, and I get an additional degree in form. And the same happens here. So this part of the data is very nice, but this here is kind of ugly. This sticks out, right? And indeed, in most of the later work, like if you look at the high gauge theory papers by John Byers and Urs Schreiber, they drop this delta. And the price that you have to pay for this is that the part of the curvature expression that you have on this gerb has to vanish, because otherwise gauge transformations do not compose properly. Yeah. Okay, and then you can really describe all this co-cycle information and very, very explicit. I mean, this is, I just flashed these formulas to show that this is all really explicit and you can X these all out, right? And then you see that the principal 1G bundle, if your group happens to be trivial, only trivial morphisms, then this is just a principal G bundle and a principal U1 over 1. So if you have just in your 2 group morphisms U1 and just 1 object, then you get an abelian gerb, right? So it's a generalization of abelian gerbs and principal G bundles to non-abelian gerbs. Okay, so but we do have this additional co-cycle condition, if you want, that says, okay, this curvature expression has to vanish on each patch. No, this is the strict expressions, right? I mean, you can I use strict gauge 2 groups, but you can also do that for semi-strict one. Just the formulas get more complicated, and if you want to do finite global expressions, they become complicated and indirect. And here, everything is very, very explicit and direct, right? Okay, so why should this expression here vanish? So you see here something that looks like an ordinary curvature and is corrected by B. This is a standard expression that you get if you do higher gauge theory. While gauge transformations do not close, co-cycles don't glue together, which is of course very bad. Then at a finite level, you see that higher parallel transport is not reparametrization invariant, which is of course something that's very bad. I originally came into these non-abelian gerbs by being interested in M5 branes, and there you want to have a non-abelian version of the self-duality equation in 6 dimensions, H equals Hodge H. And this equation is not gauge covariant if the fake curvature doesn't vanish, because the gauge transformation produces an additional term here. And you see under gauge transformation, this can produce all kinds of things that will get mixed up. Okay, so without this condition is problematic, but with this condition, you have the problem that principal 1G bundle are flat principal G bundles. That's not nice. And more importantly, and that's the big killer, is that higher connections are locally abelian. So you can show that there's always a gauge that you just gauge away all the A, and you're just left with an abelian gerb. And I think this is the main reason why, in the theoretical physics and string theory community, people don't like these non-abelian gerbs, right? Because, I mean, you easily observe that, right? So there was an analyst who proved that, and we mentioned that in our paper, how to argue that quickly. But yeah, I mean, they look very quickly locally abelian if you work with this fake flatness condition. And but there's a solution to this. And I was a little bit surprised that it took so long to get to this point. It's hidden in the literature to a certain extent, but only in very special cases. So what you have is you have your higher group. And this higher group comes with an additional algebraic datum, which is a map from G across the Lie algebra or Lie2 algebra of G to the Lie2 algebra. And this additional map, of course, has to satisfy a particular condition. And this is really an algebraic datum, because if you want to define invariant polynomials for the L-infinity algebra of this higher group, you really need to do that. Otherwise, the definition is not compatible with quasi-isomorphism, which is not nice, right? No, in the one group case, this is actually absent. You don't need it in the one. You don't see this in the one. You do see it from 2 groups onwards all the way up, right? Well, you have to find it, right? So it's still a little bit mysterious. There's a map that satisfies conditions, and you can construct this map for a lot of cases. I'll show you an example in a second. In the example set, we know it comes actually from an alternator. So if you, at least at the infinitesimal algebraic level, I know a little bit more about it. So you know that L-infinity algebras categorify the Jacobiators and the higher Jacobiators. You can also categorify the antisymmetry of the Lie bracket, and you get alternators. And if you introduce these alternators, you get the additional algebraic information that in the infinitesimal case produces this map. Okay, but I would say it's not completely well understood how this works. Also, in this T duality project, we found a group that doesn't allow for such a map, right? So this is there. It deforms the gauge, it deforms the curvature, and as a consequence, it deforms the gauge transformation for the B field. Deforms all the higher curvature except for the lowest one. Yeah, then they close. Yeah. Yeah. Without the fake curvature condition. Yes. I'll show you an example in a second, then you probably have a better intuition about it. Okay, so for connections on principal G bundles, okay, so what this kappa does now, it allows us to specify this awkward additional datum delta that we had that didn't really fit into the sequence in terms of A and F, right? You take kappa of A and F, and then you get this delta out. Roughly speaking, right? So the adjustment, yeah, okay, so it changes the curvature, co-cycle, and co-boundary relations, and it allows us to drop the fake flatness condition. So all this sounds really sophisticated, but if you look at the physics literature, they were already there, and essentially the need for an adjustment was known to supergravity people from the early 80s. If you look at heterotic supergravity, then you can describe it by a string Lie algebra, R1 infinitesimally over spin n, for example, right? You have here the B field, the gerb, and you want to couple it to non-abelian gauge algebra, right? So there's a particular string Lie algebra that does that here, written in L-infinity, two-term L-infinity notation. You get these gauge potentials, and yeah, and you have these curvature expressions. Without the adjustment, you have this curvature expression over here. You have dB plus a cubed. But they quickly realized in supergravity that this does not allow for nice gluing of things. Instead, you should add this AF term. And this is precisely the adjustment for the string n Lie algebra. And if you do this, the awkward A cube term combines nicely into the three-form, Chern-Simons three-form, right? So this is what it does in this special case. But you can do that for a lot of two groups, right? And this now allows you to get really interesting non-abelian gerbs with interesting curvatures, right? So this additional ingredient of an adjustment is the key, right? Okay, and yeah, exactly. Yes, this is exactly what it is, right? No. I mean, for example, it's still mysterious where this data comes from, right? I know that it comes from alternators in EL-infinity algebra. However, each EL-infinity algebra is isomorphic, quasi-isomorphic to an L-infinity algebra, so you don't see the alternator. So it's not completely clear where it should come from, right? I just know that these maps exist for a lot of these groups, and that it allows us to construct interesting non-abelian gerbs. Yeah, exactly. Okay, right. Oh, well, that's interesting, yeah. It would be good to understand what this is in more general terms and where it comes from, right? Unfortunately, you don't get intuition because it doesn't appear at the one level, right? For ordinary gauge theory, it doesn't exist, right? We have, if you're interested, we have lots of examples in this paper on EL-infinity algebra. So in gauge supergravity, it appears quite a bit. Sorry to advertise that a little bit more, but I think that's an important point. So in this paper here, we discussed the tensor hierarchies of gauge supergravity. And there you see the adjustment come out from H-Lie algebras. And you can precisely identify how it comes about and why it comes about. But yeah. This is the infinitesimal one, but the finite one is only, I mean, this is like this year, essentially. The finite stuff is all this year. Okay, so geometric T-duality. Right, so here we go back to Konrad's diagram or Konrad and Thomas Nikolaus' diagram of principal two bundles. And then you can identify, now let me provide a few more details. So these bundles that you have here in the correspondence at the endpoints, they are so-called principal TB F2N bundles, where this is a particular two group that's suitable for F2 string backgrounds, geometric string backgrounds. And the one on the correspondence, the one that governs the correspondence, is a principal Tdn bundle. Right? And now the nice thing is that these projections are actually not just bundle maps, but they're induced by maps between the two groups, right? The two groups, you have a map between these. Remember that the bundle is nothing but a map from the check groupoid into the one object Li2 groupoid that has these as morphisms. And you can compose these, and therefore it's quite clear how to do that even at the level of cocycles. You can do all of this explicitly. And then to get the T-duality, what you do is on this group that is a structure 2 group of this 2 bundle, you apply this flip morphism, and then you compose it again with this projection map, right? So there is this flip map that governs T-duality by just acting on the structure group of this principal 2 bundle. All right, and now you use the trick of adjustment and put on a differential refinement. That means we have control over the B field and the metric, and we've done this. And the interesting thing is now that TBNF2 does not come with an adjustment. So you write down the relation that this adjustment datum has to satisfy, and TBFN2 does not have one, right? Now you could say, okay, then the whole correspondence is lost. But actually already in the case of non-geometric topological T-duality, you don't really know what these bundles are. It's more that you want to describe the correspondence itself, and you need to be able to recover all the data from this, but it's not really necessary to really have the endpoints of this correspondence, right? We will have to content ourselves just with this big bundle from which we can derive all the data. However, Tdn comes with a very, very natural adjustment map. I mean, it's the obvious additional it's the obvious map that you would guess immediately, and this works. And then you have the full topological and full connection data on these bundles. And you can reconstruct the gerb and bundle data that you would expect here on both cases, even though we can't do the adjustment. But from this data, from this connection data that you have here, you can fully reconstruct that. And as Konrad showed us, that this reproduces also the Buscher rules, so we are fine in the case of geometric T-duality. If you want to do affine torus bundles, what you do is you just replace U1 to the n with GLNZ semi-direct product U1 to the n, and you can extend this to TDN, and then you cover also affine torus bundles without problems. And in the paper we discuss it immediately in this case, but it's a little bit cumbersome to have this factor around the whole time. So I'll drop it in the following. I'm not sure, because I don't understand adjustment fully, right? But it's a little bit like in the non-geometric case, right? You're not guaranteed that the lower bundle really exists, right? It could be that our notion of adjustment is too strict, that it's not general enough to allow for the adjustment in TBF2. It's a little bit suspicious that the topological T-duality works, but our notion of adjustment doesn't, I agree. But in a sense, yeah. Yes, exactly. Well, I mean, it says that you can't put the connection and the gerb connection, you can't package them together, in our way at least, right? There may be a more general formulation where you can do it, but we don't know how to do that at the moment. But we know how to do this PC, right? We know how to do the geometric, the correspondence to bundle, and therefore we can describe it just as well as the topological case for the non-geometric case, right? Okay. Yeah, this is just to get the affine torus. You know that Chris asked about affine torus bundle. No, that just goes through, right? There's no new data, right? There's no big mixing here with the gerb part, therefore this goes through. Okay, so the standard example for T-duality is the 3D Neal manifolds, or the 3D Neal manifolds. These are just principal circle bundles over the 2 torus. They're characterized by an integer, the first Chern class of that circle bundle. And let's describe them subordinate to the obvious cover. We cover the 2 torus by R2 and resolve U1 into R of Z, of course, as usual. And then you just identify points as follows, from which you can read off the transition function. There's an explicit local connection form. Kaluza-Klein metric looks like this. And the gerbs on the Neal manifolds are again characterized by an integer, which is why we have a very nice situation, because under T-duality we expect that the Chern class of the principal circle bundle gets exchanged for the Dix-Meduadi class of the gerb, right? So we would just want to exchange the gerb with Dix-Meduadi class L over the Neal manifold with first Chern class K gets replaced by the inverse one, right? And let's do this now with our bundle. So we have this correspondence, right? And the Li2 group is, we have one T-duality direction, so it's TD1. Just looks like this, which is very, very harmless. And what does the topological cocycle data look like? Well, it looks like this. it's very easy to write these parts down. This one was surprisingly non-trivial, so it took us a while to find this. I'm not sure why this is, but yeah, I mean, you write this down. This satisfies the usual topological co-cycle condition, and you can see that L and K appear everywhere pretty much on equal footing, right? So L and K, if I exchange them, I just get the T-duality that I would expect, right? Then you can differentially refine that. You can put connections on that, which just look like this. It's literally what you would expect. B is interestingly 0, but this is not surprising because, I mean, all the data is essentially in the gauge potential 1 forms. And this is a lambda that glues things together. It's a little bit more complicated because phi is a little bit more complicated, right? And from this data, you can develop a general procedure how you get from this data of a Tdn bundle the ordinary string backgrounds that you have sitting here and here, right? So, and we have this in the paper, but it's technical. But you see here that everything is very explicit, right? I mean, there's nothing hidden, there's nothing abstract, so you just have these functions, you have the explicit connections, and it just works. Okay, so then let's look a little bit at the T-duality group and how this comes about. So what is this Tdn and where does it actually come from? And you can get this from Kaluza-Klein reduction. And T-duality is clearly intimately linked to Kaluza-Klein reduction because in the Gaussian sequence, we had fiber integration. The metric on the total space is given by the Kaluza-Klein metric, and there's lots of literature saying that we should be doing that. Okay, so what are we doing? A lot of geometric objects are obtained from maps into a particular classifying space C, right? And if I have a manifold, and it's a trivial Cartesian product with a particular torus, and I want to map into the classifying space, I can just use the usual currying and take the Tn over here. So I get functions into this torus space in my classifying space. And if these fibrations are non-trivial, then I should take a homotopy quotient. And if you want to know the detail of this procedure, then you look at the paper by these two papers, right? So let's do that for our case, namely we start with a GERB, right? And we want to Kaluza-Klein reduce it along the fibers of a circle bundle. So the classifying space is this BBU1. So it's a 2 category that has U1 as its 2 morphism, just a single morphism and a single object. And then you can show that the cyclic loop space, its homotopy quotient, is actually replacing BBU1 by this expression here, right? So, and this is nothing but the B of the following space, U1 cross, and what I do is I resolve these 2 U1 factors into R2 over Z2, so this is why I write it like this, and I get TD1, right, which we saw in the previous example. So this is quite natural, and then I can iterate this procedure, and then you get TD2, which is U1 cross U1 to the 4, right, and resolve that again in Z4 to R4, and then you iterate this further, and then you get TDN, right? I mean, this is a nice way of getting TDN all together. So this group comes out very naturally. That's not a surprise that you should be using this one. Yes, that's not there, yeah. That's not there, no. That I swept under the rug, yeah. Yeah, the action is hard. I agree. I mean, this is just like a motivation why this is a good group, right? And a motivation for what to guess later on as well for the higher ones. Because there's a few guesses in this, and that's true. Okay, and then you can look at the automorphisms of Tdn, and this is not very hard to define abstractly what this should be, right? There's natural definition of morphisms of 2 groups. There's automorphisms of 2 groups, they form naturally a 2 group, and then you have a 2 group action, right? I mean, all of this you find in the literature, and explicit formulas for these are in the literature, and you just X out what it means. And in this case, it's very much under control, and we did this all explicitly. Really, all the calculations are done there. That's not a problem. And then you can compute the automorphisms, and Konrad has this, probably should say, because Konrad did this before us. And the 2 group that you get as automorphisms is then this one. So you have GONNZ. ONNZ is the familiar T-duality group. You get an additional, what is it, a Z2 extension, right, from this G, because we work with affine torus bundles. And then you see that we have this additional set. The G, you just have a Z2 extension of this group. Right? And you then have this additional set to n factor, right? And you can this is not really there in the string theory literature, or at least before Konrad. I've never seen that before. And this is what you get if you compute the automorphism. So the interesting thing is that GONNZ, trivially regarded as a 2 group by itself, it does not act on Tdn, which is kind of problematic because we expect our T-duality group to act on the structure group. However, this extended group, the automorphism of Tdn, of course, they do, right? And so in a sense, we extended the T-duality group slightly extended, and we recovered that from the affine torus bundle. And what's now nice is that all these transformations that you know, the transformation from the geometric subgroup, the B and beta transformation, and the T dualities, they're just NO2 functors on Tdn, right? So we have now explicit two functors that you can act with on Tdn, and they implement these transformations. So now we can arrange everything in terms of, well, things that Geo and NZ acts on nicely. Yeah? Of the structure group, right? Yeah. Mm-hmm. Yes. Well, I mean, you know that the bundle is obtained by a map from the check to groupoid in the delooping of this two group, right? And then you just compose with this map and you get the action on the bundle itself, right? So the statement is that the T-duality group is already visible at the level of the structure group, right? So it's already maps acting on the structure group. You don't even need to go to the bundle, and you get then induced maps on the bundle. Yeah, but yes, but this group will appear in a second also from a different perspective, okay? Yes, if you want, you could call it the local version, but in what comes next, this will appear explicitly, and then it's really forced to be the global thing. Okay, so groupoid bundles for T-folds. Now I should go back to this homotopy quotient, how I did the Kaluza-Klein reduction to get this TD, and have to admit that I actually cheated because of the following thing. I mean, the reduction to TD1 is still fine, but then if I want to do the reduction one step further, you know, in BTD1, I have these factors, but you see that these factors, if I take the Kaluza-Klein reduction, produce additional U1 factors, right? So I don't just get a two group, like I wrote initially, but I actually get a two groupoid, right? Because there are these additional U1 factors around, right? So this is the TD2 part that was there before, but I have also these additional factors. And this is completely clear because if I reduce a two form on a two torus, then of course I get two forms. I get, well, two torus cross along a two torus, right, in a larger dimensional manifold. I get two forms, I get one forms, and I get in particular scalar modes, right, as well. And from the B field, I get one scalar mode. From the metric, I get three scalar modes. So I expect altogether four scalar modes, and this is why I have a U1 to the 4 factor appearing here automatically, right? So at least for two T-duality directions, I automatically need to switch to two groupoids, and now I have to go beyond what Konrad and Thomas Nikolaus did, right? So yeah, so I need to extend Tdn to a two groupoid Tdn. Again, because T-dualities yield scalars from metric and two form. And then we know from string theory that scalars should live in this Narayan moduli space, which is given by this space, right? So it's this quotient of O(n) and R by two groups. The right quotient is okay, that's reasonably harmless, we leave this alone. And the left quotient is by the T-duality group. And this quotient is not so nice, so we resolve it into its corresponding action groupoid, right? So Qn is roughly Rn squared, it's diffeomorphic to Rn squared, so it should be a nice space. And yeah, I just resolve this quotient into this action groupoid. And now what I want to do is clear. How do I combine this action groupoid with Tdn? Well, I have a GeoNNZ action on Tdn. Well, not directly GeoNNZ. I have to lift it to this two group that I had. I have an action here on Qn. I have an action on this Tdn. I have to make this action diagonal. And then I put a Tdn fiber over each point in Qn, diagonalize the action on T2n, and then I get automatically two groupoid. Is that clear, or was it too fast, right? So again, the objects are Qn. I have Tdn over each point on Qn. Because I have this action groupoid, I need to diagonalize the action that I have on Qn with a natural action on Tdn. But this gives a natural two groupoid that you can just write down, and straightforward to do so. No, I mean, yeah, the scalars will locally be maps from my patches into this modular space, right? As there should be. Scalars will always live in this Narayan modular space. This is for supergravity. No, they're locally defined and they're glued together by this G, O, N, and Z transformation. I mean, here there would be really global scalars into this space, but because I resolved it in this action groupoid, there are local maps into Qn that are glued together by G, O, N, and Z transformation. Yeah, exactly. So, okay, so then you recall our descriptions of higher principal bundles, how we obtain them. Well, we have a manifold, we have a surjective submersion, and then we have our check groupoid again. And the topological principal G bundle was just a function from the check groupoid into BG. And now what we do is we just replace BG by this Lie2 groupoid, Tdn. And you can work out what this is. It's just a two-functor between two bicategories. And you can write down explicitly what this means. If you're not happy with groupoid bundles, they appear in physics in, for example, engaged sigma models. You would write down groupoid bundles. And then you can say that a non-geometric T-duality is nothing but a Tdn bundle. Okay, so that's a strong claim, so I should give you an example. Or first a few remarks and then I give you the example. First of all, the T-duality group that was fiber-wise, as you said before, right, is now actually gauged and appears not fiber-wise but global, right? But it's gauged because I have now this gluing function between the scalars, right? However, it's gauged as a discrete group, so there are no connections appearing in this. This matches what we have, the topological discussion that Thomas, Nikolaus, and Konrad had in their paper, and we can put a differential refinement into this. There's an interesting restriction that you get on this topological cocycles for the existence of adjustment. That's one of the open mathematical questions there, what this means. So this describes all T-dualities between pairs of T-folds. Right before, in the paper by Konrad, there was geometric, a T-duality that was half geometric, so you had one geometric leg, one non-geometric leg. Here we would claim that we can get arbitrary T-dualities between arbitrary T-folds, right? I mean, yeah, there's a concrete condition for getting half geometric T-dualities, so you can do that. Well, it's in transition functions are glued together by the T-duality group. Right. I mean, the transition functions are just not ordinary transition functions, but you'll see the example, my definition, in a second, right? It's a groupoid bundle. Yes, it's a groupoid bundle. The T-fold, a T-fold itself, I would say, is just a bundle into sorry, where are we? Into this groupoid. Then you can describe already T-folds. No, a principal groupoid bundle, just one. This is an ordinary groupoid. Yes, the principal groupoid bundle gives you T-fold, right? You have scalars that map into a particular space, and you glue these together with the T-duality group. Huh? Well, I mean, this is, let me show you the example. Yeah, this we did. Okay, so the nice thing before I get to the example, sorry, one second, is if you want to describe these Q spaces or T-folds, we can use higher instead of non-commutative geometry, and, well, it depends now probably what you find easier, but I would say that the higher geometric picture that we have is a little bit more accessible. Okay, so explicit example. Should stand on the other side. Okay, so now we take again the Neal manifold because, well, this is well studied in the literature. We take two T-dualities. That means our base manifold is not just one circle. We T-dualize along the fiber of the Neal manifold and an additional circle along the torus base. The gauge T2 groupoid is TD2. And this is the cocycle data. So again, you see, this is all very explicit. I mean, there's nothing scary or complicated here, right? So you have these cocycles. They satisfy some conditions. And now, okay, let's study that in more detail. The topology tells us, because we are over S1, that all data over Y3 is trivial, so we can cross out all of this data or have it trivial. And we also know that there are no Tn bundles over the circle, so therefore also psi is trivial, right? And what you're left with is now scalars that take local patches, if you want, into this Q2, which is R4. And you have transition functions for these scalars, which is given by the T-duality group, right? And these are the relations. Why do you get 4 scalar modes? Again, because you have 3 components, 3 scalar components of the metric along which you reduce, and 1 scalar component from the 2 form. And the well-known T-fold that you find all over the physics literature is just a special case where the transition function looks like this with the L down here, right? So it's really a groupoid bundle, actually. Okay, so now the last thing that's missing is R spaces. So what do I do here? Well, I mean, T-folds Q spaces were relatively harmless because they're locally geometric, right? I have to glue them together with T-duality transformations, which make them more complicated, but at least locally they're geometric. Now, R spaces are not even locally geometric, but perhaps the higher description that was good so far, perhaps we can extend it even further, and then indeed it works, right? So for one T-duality direction, we had, from the B field, it produced 2 and 1 forms. So therefore, we had Lie 2 group, Tdn bundles with connection, right? We had these 2 bundles, they have 2 and 1 forms as potentials. For 2 T-duality direction, the B fields will split up into 2 forms, 1 forms, and 0 forms, right? And because we had the 0 forms around, now we also had to introduce scalars, and that led to the Lie 2 groupoid bundles with connection that we had before. Now, if we continue that, if we have 3 T-duality directions, then the B field will produce 2, 1, 0, and -1 forms. Of course, -1 forms doesn't make sense. However, -1 forms have a global curvature 0 form, and we can still hope to describe these -1 forms by their global curvature 0 forms, right? But these are now global. I mean, remember that the scalars were local. They were glued together by the T-duality transformation, so they were local scalars. But these here can now be really global 0 forms. And that is the hint that what we actually should be doing is should be using an augmented Lie 2 groupoid with connection. And let me explain this. So we switch to simplicial picture, and there we regard higher groupoids as Kahn-simplicial manifolds, or well, higher Lie groupoids, I should say, as Kahn-simplicial manifolds. And higher groupoid 1 morphism are simply simplicial maps, and higher groupoid 2 morphism are simplicial homotopes. And then you get these quasi-groupoids or quasi-Lie groupoids or infinity 1 groupoids, right? So that's a very nice description if you have to work with higher categories and you don't want to work out explicit coherence axioms and so on. But on the other hand, you pay a price, namely there's a lot of redundancy in this data if you write it out what it explicitly means, right? So now what can we do? Well, we have here our check groupoid for a particular surjective submersion, for a particular cover if you want, right? The fiber product here. And in the simplicial case, I have to go to the nerve. So here I have the double fiber product or whatever you want to call this. And it continues then all the way to infinity, of course. But instead of just stopping at this point, I do have this additional map sigma, which allows me to go 1 step further and introduce like -1 simplices, right? And these are called augmented simplicial sets, and they are found in the literature, right? So the check groupoid allows very naturally to augment. And what I can do then is I can also say, well, I mean, the Lie 2 groupoid that I introduced before, I can also augment that by -1 simplices. And then I will get a global map as I expected previously, right? And then you see very nicely how the picture developed, right? If G2 and G1 were non-trivial, then I'm in the geometric situation, right? Just 1 forms on 2 forms. Or well, let's start from H3 actually. If I just have a gerb, then just G2 is non-trivial, right? All of these are trivial. And then I just have a gerb. If I dimension reduce 1, I get also 1 form potentials. So I better also include G1, right? So I get a principal 2 bundle. If I get scalars, I also need to have a scalar manifold. So I introduce G0 right here. And if I now also want the -1 forms, I better introduce their global curvatures. And then I introduce G-1. And then I have this total picture, right? So we really nicely extended this picture. And of course, I can restrict again all my information in such a way that I just see the geometric parts. If these maps are trivial, I always go back to the simpler cases, right? So the picture is really growing, and everything that I told you before is always included in the next step. The orbit space? No, in principle, you can put something here that what you want, right? I mean, there's a question what to put there. And Right, yeah. Yes, that's true. No, that's not what we put there. Yeah. Yes, but this is not what we put there, actually. Well, I don't think so. To check that. Yes, but in this case, yes. I mean, in this case, yeah. I mean, we do have to augment by a suitable space of these R-fluxes. These are now which enter the picture. And to determine those, I mean, I don't see it so quickly. I have to think a little bit about it. But see if that leads to, yeah, pi 0. I mean, what we did is we looked at the tensor hierarchy that appears in supergravity for in this situation, and in this gauge version of supergravity, there's this embedding tensor, and that gives you a particular representation, and then you have all kinds of other representations of the T-duality group, and that gives you a hint of what you actually want to put there, right? So just from physics consideration, we guessed what we want to put there, and I think we believe that this works, right? And then this whole issue of augmentation and differentially refining it, that's fairly trivial. You can really just write down what all of these things should be, okay? So again, you can write down explicit example from Neal manifolds. We did this in the paper if you want to see the details. And then you get all kinds of interesting consistency conditions between the Q and R-fluxes, right? I mean, usually in the physics literature, I think at least in what I've seen is you have either Q or you have R-fluxes. But here you can combine these now, right? And then you get additional consistency conditions between when this should be okay and what you should be doing. And importantly, as I said, all the previously discussed cases are included. So, right, I mean, you can, if you have such Tdn augmented bundles, they include in particular the Tdn bundles. They include the Tdn principal 2 bundles and so on, right? You can always reduce. And all of that actually can be extended trivially to affine U1 bundles. That's not a problem. Right, so to describe R spaces, you can either use these higher geometries or you can use non-associative geometries, right? So but at least it's an interesting perspective possibly to replace non-associative geometry just with higher geometry, at least in this case. Well, it's a generalization of, well, it's vague, right? And this is an exact definition, of course, right? So I would say a Tdn bundle contains what physicists call an R space, right? So physicists would describe it in terms of non-associative spaces, in terms of, yeah, what's Richard knows that, right? Mm-hmm. Yes. Mm-hmm. Exactly, yeah. Mm-hmm. Mm-hmm. Yes, absolutely. Well, this Tdn bundle, of course, is essentially the increased space, right? Because the fibers contain T2n, right? And if you linearize that, it's essentially double field theory, right? The fibers are contained in this bundle. Yeah, we didn't link it up, but in principle, yeah, it's a linearization of the fibers of these bundles, of course, yeah. Well, we have the Neal manifold example, and we see that this works. Right, I mean, we show that we get the right R fluxes. Yeah, we should probably discuss a little bit further. Yeah. Yeah, I mean, we can write down the full co-cycle information from which you should be able to reconstruct exactly your metric and your B field, right? Okay. But yeah, I mean, in this sense, at least you have something very concrete, mathematically cleanly defined what an R space could be, right? So that's yeah. Okay, but let me summarize. I'm doing for time. Yeah, so 5 minutes, okay. So what has been done is that we show, well, topological T-duality can be tried using principal 2 bundles, as Konrad told us. There's a differential refinement that is using adjusted curvatures, and adjusted curvatures, again, to advertise them a little bit more, they make principal 2 bundles or non-abelian gerbs fun. They take all the problems of the fake curvature out. There's an explicit description of geometric T-duality. At least with Neal manifolds, we can make everything very, very explicit, and you see the T-duality really happening there at a geometric level with differential refinement. The T-duality group is really a 2 group derived from KK reduction, right? And then you can extend our picture of T-duality to Q spaces, T-folds, and R spaces. Yeah, so future work is we clearly need to link much more these mathematical results or proposed mathematical constructions to physical expectations, in particular then to double field theory and old hobby, these pre-NQ manifolds. So there's a differential graded description underlying DFT and to link this up. And then the question, of course, can you do something non-abelian? A non-abelian T-duality there. I'm not so sure if that works in this picture. I mean, there's a couple of reasons to believe why. There's at least you see immediately certain problems and certain difficulties in generalizing that. But more interesting is probably U-duality, because there we already have the infinitesimal picture completely under control. We know exactly what these adjusted curvatures are in all these cases. And we hope that we can build something up there. The problem is that we here used heavily the technology of bicategories, which is still relatively harmless. But if you want to do U-duality, because you start from a 2-gerp, you need tricategories, which are less pleasant. And yeah, it's not quite clear how much we can get this situation under control, but this is next on our list, certainly. Okay, thank you very much.